Hello and welcome to the TI Precision Lab video discussing the basics of brushless DC motors, also called BLDC motors for short. In this video, we'll discuss fundamentals of BLDC motor operation, construction of BLDC motors, and the circuitry needed to drive BLDC motors. First, let's cover the fundamentals of BLDC motor operation. An easy model of a BLDC motor is a permanent magnet on the rotor of the motor, which is surrounded on the stator by coils that act as electromagnets when current is injected into them. By successively injecting current to different coils, a moving magnetic field is generated that continuously drags the rotor along the circle. This is the basic concept of how a BLDC motor is spun. This process of switching which coils have current injected to generate motion is called commutation. BLDCs are three-phase motors with three input connections to the phases labeled A, B, and C. The diagram on screen shows the three motor phases wound as coils on the stator to act as electromagnets when current is injected into them. For every motor phase coil, such as phase A coil, there is an inverse phase A coil across from it wound in the opposite way, which induces an opposite electromagnetic polarity. This is how we are able to equally attract or repel the opposite polarity sides of the rotor. As depicted previously, the changing of which phase stator coils are injected with current or commutation generates a moving magnetic field that continuously drags the rotor along the circle. The big distinguishing factor between brushed and brushless DC motors is commutation. In brushed DC motors, the commutation is automatically handled by the motor's mechanical design, and you can learn more about brushed DC motors in the module Brushed DC Motors 1 Basics. In brushless DC motors, the commutation needs to be decided by the motor driver circuitry using feedback of rotor position from the motor. The feedback mechanisms will be covered in our future video in this series. While the brushes on the brushed DC motors result in less complexity for the motor drive's electronics, the brushes can cause high heat dissipation due to the compact construction of the motor. The brush commutation can also cause sparking as the brushes make and break contact, which negatively affects the lifetime of the motor and can also cause EMI radiation. While the brushless DC motor avoids all of these issues, it does require more complex motor driver circuitry to be able to properly commutate. Now let's focus on how a BLDC motor is wound. BLDC motor construction can vary in winding connection of its three motor phases. Shown on the left is the WYE winding or star connection, and shown on the right is the delta winding connection. A WYE or star connection is the most common winding construction. An important thing to keep in mind is that regardless of the winding, both motors are driven in the same way. The WYE winding typically is more efficient, has less resistive losses, is more immune to parasitic currents, and has higher torque at low speed. The delta winding's main advantage is higher top speed. Back electromotive force, also known as back EMF, is a voltage in a motor phase that opposes the change in current which induced it, and is used in some sensorless motor control drive algorithms to indicate rotor position. The topic of back EMF will be dived deeper in future videos in this series. BLDC motor construction determines whether the motor has sinusoidal shaped back EMF, shown on the left, or trapezoidal shaped back EMF, shown in the middle. Back EMF shape is important because it will determine the motor control technique that is the most efficient to use. We will discuss this in greater detail in future videos in this series. In order to see back EMF shape of a motor, just connect an oscilloscope voltage probe across two phases of a motor, spin the motor rotor, and see the back EMF on the oscilloscope. When the permanent magnet on a BLDC rotor has more than one pair of north and south poles, also referred to as pole pairs, there is a difference in the two concepts of electrical cycles and mechanical cycles. A mechanical cycle is the time for a motor rotor to travel one full revolution, as shown in the animation on screen. Typically, when people refer to the speed of a motor, they refer to the mechanical cycles. An electrical cycle is the time for a rotor to rotate through one set of pole pairs, as shown in the animation on screen. The reason why electrical cycles are significant is that in some methods of motor rotor position tracking, rotor position is detected in terms of electrical cycles. As one can infer from the description of electrical and mechanical cycles, one mechanical cycle is equal to an electrical cycle times the number of pole pairs. Correlating that to speed, the equation for mechanical speed is equal to electrical speed divided by the number of pole pairs of the permanent magnet rotor. Now we'll go over the typical circuitry required for driving a BLDC motor. The circuitry needed to drive a BLDC motor consists of 5 modules. The modules include a control block, 3 half-bridge circuits that apply power directly to the motor, the gate drivers that allow the control block to interface with the half-bridge circuits, motor rotor position sensing feedback to determine commutation, and any protection circuits. Let's deep dive into each one of these modules. Each of the 3 half-bridge circuits are indicated by the dotted boxes. Each half-bridge circuit consists of 2 MOSFETs in series with their junction connected to one of the 3 motor phases. The half-bridge circuits can either connect the motor phases to VCC or ground, and do this in such a way that current can be injected or energized in stator coils, as indicated by the red dotted line. The ability of the half-bridge circuits to switch which phases and stator coils are energized is how commutation is accomplished. A moving magnetic field is generated and a BLDC motor is spun. Gate drivers are the circuitry connected to the gates of the MOSFETs used to turn them on and off. Motor drive devices can either integrate just gate drivers and use external half-bridge circuits, or may integrate both the gate driver circuits and the 3 half-bridge circuits. Gate drivers will be covered in greater detail in future videos in this series. Because commutation in BLDC motors isn't automatically done by the mechanical design, there needs to be a control block that dictates commutation and controls the gate drivers. The control block can come in many forms, including an MCU, FPGA, DSP, digital state machine, or pure analog implementation. Because commutation is dictated by motor rotor position, the control block needs rotor position feedback. This rotor position feedback can come from external sensors such as encoders and Hall effect sensors, or it can be derived from motor voltages and currents such as back EMF in a sensorless fashion. Different rotor feedback systems will be explored in future videos in this series. During motor operation, there are many situations that might damage the motor driver or motor itself, and therefore it is important to have protection circuitry. Overcurrent protection, or OCP, stops motor current from crossing the rated limits. Thermal shutdown stops motor operation if the motor driver exceeds its rated temperature. Under voltage lockout, or UVLO, protects the motor control circuitry from the supply voltage dropping below the operating range. Shoot-through protection circuitry helps prevent both MOSFETs in a half-bridge circuit from being on simultaneously, which would result in a current short. Lock detect circuitry determines when the motor is stalled. Anti-voltage surge protection, or AVS, helps prevent energy from being pumped into system supply by the motor. Motor's protection circuitry will be explored deeper in future videos in this series. To find more motor driver technical resources and search products, visit ti.com/motordrivers.